first law is obeyed. The plate loses gravitational potential energy. It gains kinetic energy. It speeds toward the ground. When it strikes the ground, what does it do? All that energy becomes heat and noise, and this plate shatters, and the bonds that held the plate together are broken, representing an input of potential energy. Are you picturing this? Yes? Now let's see it backwards. Shall we see it backwards? Let's picture it backwards. Sound energy and heat from the floor at first are chaotic and random, but they get more and more concerted, right? In a concerted effort, they begin to vibrate in unison, right? Propelling pieces of plate on the floor suddenly, like little rowers in a little bitty ship, right? The molecules on the floor move in the same direction, all heave-ho, and they hurl these fragments of plate back together. Are you picturing this? At the same time, sound from the walls were warm, right? The walls cool down and generate sound, which focuses magically on this collision of the plate and the floor, right? Those particles come back together with exactly the right velocity and exactly the right energy to reform the bonds that made the plate in the original place, right? Giving the plate a certain vibration or torque so that it flies off the ground and lands on the table. Yes?
Yeah.
None of this violates the first law. All of the energy that was released is put back. Yes? How about the second law? Are we violating that? Yeah, I'm thinking we kind of violated that, right? We went to disorder. The plate all smashed up, all of that energy spread around as heat, and we made it very orderly. All of the energy is in this thing sitting on the table, right? Yeah. Okay. Yeah. So in that way, we actually decreased the order. How about this is the story I'll tell. My dad used to teach this class on French films, right? You could teach anything you want. He taught Shakespeare, but during the month of January, you taught this block class. So he taught this class on French films, yes? And so they would sit there, and they had this great projection. They had a rear projection screen in the humanities building. So they would project these images from behind the screen. Who's sleeping? They would project the images from behind the screen, and you could sit up really, really close to the screen. Oh, I'm sorry. Well, we'll wait till he falls asleep again and light a firecracker. Okay. They would project the images from behind the screen on the screen, and the weird thing is that you can't really, if it's a forward projection screen, you can't sit too close to it and see the image. Why not? Because it's coming from behind, and you would block the light, wouldn't you? Yeah, now rear projection screen, you could just sit there with your nose up against it. So there was a relatively small little place where he would show these movies, and I don't know what they would do. They would watch the movies and then say like intelligent English major type things about them or something like that, right? Okay, so there's a scene, and the scene was a voiceover. Okay, a voiceover means they film the foreground scene, the voices are added later. Yes? Do we know this about film? I guess this is sort of something that's lost about film, right? Okay, so they filmed this scene, and the scene was a woman's arm flung out of the bed with a cigarette in the arm, right? Okay, and apparently the woman and the man had been discussing taxes or finances shortly before this scene was filmed or something. I really don't know what would happen before this scene, right? But anyway, the man goes through the door, and there's a conversation in the other room that you can hear. That's the voiceover, right? And this hand is flung out. There's a cigarette burning, and the close-up is kind of on the cigarette. Well, the kid is sitting right in the front row looking at this thing, right? And they notice that the cigarette's kind of unusual. The smoke is going into the cigarette. If you get close enough, you can see that, right? It's not just smoke, it's going into the cigarette. Ashes, presumably heat, is also going into the cigarette and making tobacco, right? Out of the ashes that sometimes fly up from the floor and glue themselves onto the cigarette. Yeah? Is that likely to happen?
No.
No, not so much, right? So what did they do? What happened?
They were very small.
Yeah, they dropped that piece of film on the ground. Like, oop, crap, which way is it, right? And they had a 50-50 chance of getting the right end spliced in there, because literally film was you spliced it together, right? You honest to God cut it with scissors, put it in there. There was ways to do this, yeah? Right? Now, here's how it was possible. Normally, film has a voice track on it. Voiceovers don't. A voice track makes it irreversible. The voice track's on, like, say, the left side of the film, right? Have you ever seen it? It's like a little, the audio is made into a picture on the film, and so a photo cell can read the audio track off the film. This is a crazy thing, right? Okay, but since it was a voiceover, it had no voice track on it, and they dropped it and they put it on backwards. Isn't that funny? Yeah. So entropy is sometimes called time's arrow. Okay, it shows you which way time is going. right? If you see a film of a car unwrapping itself from a telephone pole, going back up onto the road, and then going backwards at 60 miles per hour, you know that's probably not what happened, right? Yeah? Yeah, yeah? Okay. Possible, but not too likely. Yeah, it's impossible. I mean, it's, at some probability, you just say, no, that's not going to happen, right? Okay. I took a whole class on this. Okay, this is called statistical mechanics in physics. It's also called physical chemistry in chemistry. Yeah? Okay. And then the third law is, the first one is you can't get something for nothing. The second one is you can't even break even, right? You can't even do this. You can't even break even. And the third law is you can't get out of the game, right? You could get out of the game if one of your temperatures was absolute zero, but you can't do it. This is sort of beyond the scope of a high school classroom, but we can look at it this way. You can calculate the efficiency. This is called the Carnot cycle. We don't do this formula anymore, but we used to do this formula. This talks about the efficiency of a heat engine. And basically, the bigger the difference between your high temperature and your low temperature, the more efficient an engine is, right? And this, but even then, it cannot be more efficient than this, right? That's why it's called I'm just joking, it's a Carnot cycle anyway, right? Now what if this is the cold temperature, that's the high temperature? What if your cold temperature is absolute zero?
Zero.
Then that's zero, TH minus 0 over TH is an efficiency of 1. You've now violated the second law of thermodynamics. You've turned all of a certain amount of heat into all a certain amount of, that would be 100% efficient, right? Okay. Yeah, first law is no problem, right? Okay. But this would, if you could do that, you could actually violate the second law, and you can't do that. Okay. One way to explain it, right, is as you approach absolute zero, you actually have an infinite probability of gaining heat, right? Well, infinite probability, or your probability is unity, right? Not infinite, but 1, right? Yeah. There we have it.